So yesterday we have completed the chapter hydrocarbon, and today we will start with the haloalkane, haloarine, or you can say organic compounds containing halogens. So this is the JEE syllabus that we are having. So it basically include the properties and reactions of this, say haloalkane and haloarine, and some of this polynuclear compound, including this chloroform, means polyhalogen compound, including this chloroform, iodoform, freons, and etc. We will also be seeing some of the reaction mechanism like SN1, SN2 in short, because we have covered that in the GOC part, but we will giving a brief view of that also. So let us start our chapter. So before that, let us see the topics that are to be covered in a more detailed way. So first we will see the nature of CX bond. Then we will see its preparation from halogen, silver salt of carboxylic acid, alkene, alcohol, halide exchange method, then some other common methods. Then we will see some of the reactions. So we will see the chemical reactivity. Okay, so you see their hydrolysis and some reactions that are related to haloalkane. So, and at last we will see some metal reactions. Okay, then we will conclude our this lecture with this so-called SN1 SN2 and comparability. So children often get confused when to use SN1 and SN2. So I made a flowchart for that. So you can use it for reference for means most of the reactions that whether it will be even E2 SN1 or SN2. So coming to the weightage, so average of one question is asked from this halogen and it is of 4 marks weightage. So first of all, let us start with the nature of CX bond. So what is halogen? So halogen is something which contains halogen as a connected to carbon. So halogen includes fluorine, chlorine, bromine and iodine. So these are the four halogens that we have, and it is in the increasing order of this, say, so this is the increasing order of the atomic radii. So atomic radii increases in this order because we are going down the group, sorry, down the group. Now moving to some of the properties of this alkyl halide. So they are insoluble in water because they're not that much polar, and some sort of polarities of course developed in this haloalkane because of this X and C, this electronegativity difference between C and X, that is halogen and carbon. So there is a delta positive charge on the carbon and delta negative charge on this halogen. Now due to this reason, this charge development, many of the occurrences can happen. The first of all, the boiling point of the haloalkane is higher in comparison to corresponding haloalkane. Like suppose we have a say compound CH4 and we have this CH3Cl, then CH3Cl will have a higher boiling point. Why? Because this is having a dipole moment which is going from this carbon to this halogen, and we are having a dipole dipole kind of interaction because next molecule that we will have like CX again, this will just have an interaction like this with the other say haloalkane compound, and due to this interaction some kind of energy is released, energy is required to say boil this or convert this haloalkane into vapor. Now coming to the bond strength, so this is the order of bond strength CF, Cl, Cbr and Ci. So this is a very common bond strength. Why? Because of the decreasing size of this, say iodine, bromine, chlorine and fluorine. So fluorine has the shortest bond length. Now alkyl fluoride tends to be less reactive than any other alkyl halide due to this short bond length. So this was all about this nature of this CX bond. Now let us move to some preparation. So first we will see preparation from halogens. So we will directly react this haloalkane with halogens and see what will the product. So we will take this C2H6 in excess and react with Cl2 in presence of H nu. Then we will get this one as the major product, and many of the minor products are also formed. So if this is C2H6, so it can be possible there can be dichlorination of this same compound, that is ethane, but this ethyl chloride is formed in the major amount. Now this reaction proceeds through the free radical mechanism because this is H is present here. So first it breaks this Cl into Cl dot and Cl dot, means two radicals. Now this Cl dot react with HCH3 to give us this CH3 dot plus HCl, and now one of this radical that is released here, it reacts with this CH3 dot to give us CH3Cl, which is this. Suppose if it is methane, methane, then this will be formed. In case of ethane, this will be formed. Now if you write the step, so this is the initiation, this is the propagation, and this is the termination. So I have not mentioned in the slide because we have discussed this in the hydrocarbon, where we have seen the reaction of the hydrocarbon with the halogens. Now if we consider the reactivity of this halogen, so this is F2, Cl2, Br2 and I2. So F2 has the most reactivity, then the Cl2, Br2 and then I2. Now coming to the reactivity of alkane, so 3 degree alkane, 2 degree and 1 degree. So why is it so? Because the radical which will be formed upon reaction of the Cl, so in the second step we are seeing the propagation step, that the Cl dot is reacting with the methane. So if it is a secondary carbon, then the reactive, means is it the tertiary carbon suppose, then the compound that is formed will be more stable, or the intermediate that is formed will be more stable, because 2 degree, 3 degree radical is more stable than 2 degree, and then comes the 1 degree because of the hyperconjugation structure. So this was all about the halogenation of this haloalkane in the presence of light, that is H nu. Now we have another method from halogen, so we'll use hydrogen halides. Okay, so this is for with the sulfur chloride. Okay, so we'll use this SO2Cl2 in the presence of H nu. We will get this SO2 as a gas and HCl. Now this reaction is fast in the presence of light and traces of an organic peroxide. So if you see in this if you see in the NCRT, heat is given here in place of this H nu and organoperoxide. So if heat is supplied to this reaction, then SNI type of reaction takes place, and one base is present here. So in presence of heat and base, this goes through a SNI reaction. But if we take it the H nu and peroxide, then it will follow a radical mechanism. So this one is following a radical. So radical is formed in this reaction, and we know very well that radical are very reactive due to the same as unpaired electrons, so they react very fast. So this reaction is more faster than the than the base and heat, means conditions. Okay, now let us move from silver salt of carboxylic acid. So the order of reactivity is just reverse. So we have the 1 degree, 2 degree and 3 degree. So what we take is, we take 2 moles of this alkyl carbonate salt. So we are taking a carboxylic salt, or 2 moles, and we are reacting with I2. So we will get this ester plus 2CO2 plus 2 AgI. Only bromide is obtained in good yield, no suitable for chlorination because yield is poor. In this reaction, iodine forms ester, okay, of alkyl halide, and in the next step, reaction is called Berman-Simon reaction. Now from alkenes. So from alkenes, we are adding here HBr. So alkene can react in 2 ways. First is the Markovnikov, and second is the anti-Markovnikov, or which happens due to the presence of peroxide and is called as Kharash effect. So in this case, addition of Br takes place as this at this side. Now if we use the peroxide, then the reactant will be reversed. Okay, so addition of HBr to alkene in the presence of organic peroxide take place due to peroxide effect. The addition takes place by 2 mechanisms. Peroxide initiates free radical mechanism, Markovnikov addition by electrophilic mechanism. Okay, so this is the Markovnikov addition. So it takes place from the formation of carbocation, and in Kharash, in this peroxide, it takes place through this radical mechanism. So in radical mechanism, this Br is added at the last, and in this Markovnikov, so this one is the Markovnikov, so it's added in this secondary carbon because secondary carbocation is more stable. Now we can do it from the alcohols also. So this is the groups method that we have. So basically we are using this ROH and HX. Now we are using a base and hydrous ZnCl2 to remove this H2O. Sorry, this is not a base, this is just a thing to create less moisture. So it is used to create less moisture. Now this lone pair of O, okay, this lone pair of O, sorry, this lone pair of O will react and give us, so this is the reaction if we consider, so this is removed. So since we are using a dehydrating agent, that is anhydrous ZnCl2, so this H2 will be removed and RX will be formed. Okay. Now let us see the reactivity order. So Hi is more reactive, then HBr, then HCl, and then HF. If we consider the reactivity order of alcohol, it is 3 degree, 2 degree, 1 degree, and then MEOH. That is methylating agent. That is methyl alcohol. Now 2 degree and 3 degree alcohol undergo, whereas 1 degree and MEOH go SN2 mechanism. So 2 degree and 3 degree go SN1. Sorry, SN1 is not written here. And MEOH goes in MEOH, and this 1 degree go as SN2 reaction. That is in one step. So concentrated HCl and anhydrous ZnCl2 is known as this Lucas reagent. So this reagent is used to say determine that which alcohol is 3 degree and which is 2 degree and 1 degree. If we get this reaction in faster, so this is 3 degree, then it is slower for 2 degree and it is much more slower for 1 degree and at MEOH. So basically we rise the temperature. As we increase this temperature, the reactivity for 1 degree we need a higher temperature, then for 2 degree we need a lower temperature, and for 3 degree we do it at room temperature. So in this way you can classify this say 1 degree, 2 degree, and 3 degree alcohols. Now we can also do it using this PCl5 or PCl3. So what we will do, we will react this thing with PCl5. We will get this this haloalkane, POCl3 and HCl. Now bromine and iodine derivatives cannot be obtained from the above reaction. So we cannot use this PBr5 and PF5 because PBr5 and PF5 are unstable. This method gives a good yield of primary alkyl halide but poor yield of the secondary and tertiary alkyl halide. So this does prove that the reaction takes place through SN2 reaction. Now third, we have a unique method, so I have put up this from my side. Sorry, so this is just name I have put up from my side. So this reaction is given NCRT. So I have told you earlier that we can use a base. So this is the same reaction. We are using a base instead of HNO and peroxide, and we are getting SO2 and HCl. Means the products are same, just we are changing the conditions to get different kind of mechanism. So the first one was following a radical mechanism, and this one is following a SNI mechanism. Now we have seen in every reaction that fluorine is not formed in most of the reactions. So we will suggest some method which gives us fluorine and iodine both. So this is for Finkelstein. So we are using RX and Ni. So we are doing a halogen exchange here. So this is Na having iodine, and we are having R as X as Cl or Br. Now if you react this, you will get Ri, that is alkyl iodide, plus NaX, and X is equal to Cl and Br. So if you so for fluorine we use this Schwarz reaction. So we take the salt of this mercury, means fluoride salt of mercury, okay, and we react it with say the alkyl halide to give us the following product. So we are taking a chlorinated alkyl and reacting it with Hg2F2, and we are getting this fluoride alkyl. We can also use this antimony, so it is SbF2. We can also use this, okay, so you can use this and also carry out this Schwarz reaction. Now here are some common methods that are written here, so you can remember this, it will help in transformation. So we will take a ROH, Ki and H3PO4, then we will get the similar reaction. So what will happen? So this H3PO4 is acidic in nature, This will protonate this alcohol. Now this I minus will attack this R and will get this Ri. Now the second method, the rider method that we have here. So we are using this, say this P3H5. So this is a reaction, we will get this Rx. Then again we are using a dihalide. So this is a reducing agent. So it will reduce this halide, okay, to give the Rx. Now also we can use RMGX with X2 and ROR with PCl5. So these are the reactions. So furthermore reaction that you can remember for the future references. Now we'll move to the chemical reactivity. So what makes this halogen or haloalkane reactive? So the main thing for the reactivity of this is the CX bond, means polarity of the CX bond, which allows the coming of nucleophile to this C bond. Okay, so now nucleophile, sorry, yes, electrophile, sorry. The nucleophile can come to the carbon, they can attack the carbon, and since X is a good leaving group, if it is chlorine, bromine, and iodine, we get the required product. Now, the alkyl halide are highly reactive. The order of reactivity is, so we get iodide is much more reactive than bromide, then chloride. Okay. Now, similarly for tertiary, secondary, primary. Among the primary alkyl halide, the order of reactivity. So, if you are having a primary alkyl halide, there is also an order. So, the methyl halide is much more reactive. Then we have the ethyl, and then we have this propyl. Now let us move to the hydrolysis. So we are doing the hydrolysis of this alkyl halide in the presence of this salt of silver. So we get this alcohol. Okay. Now we can also use this KOH. So in the basic condition, then we also get a alcohol. So we are using a different metals only. So we're just changing the metals. First we are using silver. The second we are using potassium. So we are getting the same product. Beside this salt that we are getting of halide. Now with the help of this reaction, an alkene can be converted into alkyne. And how? So what we will do? We will take two halides. Say we will take two halides, and then we will add HBr to it. So what we are doing, with the help of this reaction, an alkene can be converted into alcohol. Alkene is first reacted with HBr. So alkene is first reacted with HBr. So since we are using no peroxide, it will add on this side. Okay. Now since this is ethyl, so both of the carbon are equivalent in case of stability of the carbocation. So it can add on any side. And now we will take this AgOH. It will simply form this product, which is ethyl alcohol. Now some reactions that we can see. So we are taking RS. Okay, so we are taking NaSH and Rx here. Now this SH minus will act as a nucleophile, and it will attack this R, and X will leave, and we will get RSH. So this is called thioalcohol or alkane thiol or alkane mercaptan. Plus we will get this sodium halide. Second, we will do a reaction with potassium nitrate, or we can also do it with silver nitrate. So we can use both. So it can be both. So we can use Ag also in place of this. Say we can use Ag also in place of this potassium. So we'll react this thing with say Rx. So this ONO, so this will act as a nucleophile. ONO having a negative charge. This will attack this R, and this X will leave, and we will get this KX and alkyl nitrite. The third one is the sodium acetylide. So these are just some nucleophilic reactions. So we are taking different nucleophiles. The first is SH minus, second is NO2 minus nitrite ion. The third is the sodium acetate. So sodium acetate is this method is used for the formation of alkyne also. So this is the thing that we are having. So how you can form it, I have told in the earlier class also. Suppose that we have a alkyne. We have alkyne like this. So what we will do, we will simply react it with NaNH2. Now this is a strong base. It will extract a proton from this alkyne. We will get Na plus plus and C2H minus plus NH3. Now this CH2 minus, that is C2H minus, that is formed here. It will act as a nucleophile. It will attack this R and X will leave and we will get this alkyne here. Next is reaction with methane, metal. So if we take a lithium, 2Rx with lithium, so we'll get this RLi plus LiAx. Okay, so here is the example of transmetallation. We are changing the metal, so we are using Li. So sorry, this is not transmetallation. This is just a reaction with metal. So we are taking again a halide reacting with lithium and getting C2H5Li and LiBr. What if the case? So this important reaction is missed here. So if we take this C2H5Br plus Mg, okay. So this is the case of substitution. So this lithium is substituting this Br. But if we take this Mg, so since it is not that much ionic in nature, so it will do the insertion reaction. So it will be getted inserted. So it will get insert between the metal and the halide and form this so-called famous Grignard reagent, which is named after the famous scientist Victor Grignard. Now this Grignard reagent is a very useful say means substrate which is often used as a nucleophile to form the higher alkane or higher nucleophiles. So this is the reaction with metals. Now we'll see some specific metal reactions which are named Wurtz, Wurtz-Fittig and Fittig. So here I have taught some of the portion of this haloarene because it is important to teach it now for the comparison process. So the comparison, say the comparison means to compare this thing. I am teaching all these three, which also includes haloarene at the same time. So the first one is Wurtz reaction. We take alkyl halide, 2 moles of alkyl halide, and we get the means these two are connected. Second case we have here, we take one aryl halide and one alkyl halide. Now this R will get added to this aryl halide, which is called as Wurtz-Fittig reaction. The third one is Fittig reaction. So we take both of the mole as aryl halide, then we will get as diphenyl in case of if we are using this benzyl halide and plus 2NaX. So this all of this reaction takes place in the presence of triether. Now we have three reactions. Wurtz reaction, which is the combination of two alkyl, and both alkyl are same. Wurtz-Fittig, we are taking a haloarene, we are taking a haloalkane, and this aryl and alkyl group join together. Fittig reaction, we take two aryl halides, and both of the aryl groups get added, and both aryl groups are same. So this is a specific type of metal reaction. So I've just done a proper comparison of all these three. Now let us move to SN1, SN2. Okay, SN1, SN2, and then E1, E2. Now this is so this is SN1, and this is sorry, this is SN2, and this is SN1. Now SN2 is a bimolecular reaction, by which I mean is a second order reaction. So it depends both on the concentration of the both of the depends both on the concentration of both reactants. Okay, so this is the nucleophile and this is the electrophile. Now this is stereospecific in nature, so we get the inversion. So suppose we have R configuration of this haloalkane which is being attacked, then we'll get S, and if it is S, then vice versa. Now if we consider the substrate, so we since it depends upon there is a direct attack and there is an inversion thing. So if we are having say means steric hindrance, then it will be inhibited. So methyl is reacted fastest, then 1 degree, then 2 degree, and now no SN2 take with SN3. So this should be kept in mind. So never thought ever that 3 degree can go through SN2. Okay. Now considering the nucleophile, since it depends also on the nucleophile. So if you are taking a strong or a moderate nucleophile, then and then only this SN2 can take place. Otherwise, it will not take place. So this is also an important point. So we can derive it from this, or you can say it from this rate law. So it says that the rate of reaction depends upon nucleophile also. So you must at least have a moderate one, or if it is strong one, then it is good enough, but not with the weak nucleophile. So these are the list, you can remember it. So moderate one and the strong one. Now what about the leaving group? So it is moderately important, not that much important, same trend as SN1, and it happened in polar aprotic solvent. So if you have a polar aprotic solvent, it will be much more supported. Yes. Now next, the SN1 reaction. So it takes place in two steps, and the rate of reaction only depends upon the substrate or the alkyl halide that we are taking. Now there is loss of stereochemistry since carbocation is formed and the upcoming nucleophile can attack from both sides. So we get R and S both depending on the stability of the product. One will be formed in majority, another will be formed in minority, and there is no such consideration of the say steric hindrance. So while we are attacking this is in SN1, you will not consider the majority by looking at the steric hindrance, because steric hindrance is absent, is not considered for SN1. We will only see the stability of the final product. If the final product is much more stable, then it will be formed in the dominant form. Now benzylic is formed faster, because if it is a say benzylic like this, now if you form a radical, sorry, the carbocation, it is stabilized by this benzene ring. Now allylic, it is also stabilized by this resonance. Then 3 degree, then 2 degree, which are stabilized by this hyperconjugation. Now no 1 degree or methyl can undergo this ascent one unless until there is the extra stabilization of this oxygen group. So suppose if we have a electron donating group in the right side, in the side of this 1 degree, then in that case it can go through SN1. Now since this rate of reaction does not depend upon the nucleophile, so it is not important also. Now very important this thing is, it depends upon very importantly on the leaving group, because during the formation of carbocation there should be a good leaving group so that it can leave. Now the coming to the good leaving group, we have OTF, OTS, OMS, I, Br and Cl, and it happens in polar protic solvent. Now coming to this E1, so it is same as SN1, SN2. So means you can say that it is not that much different in case of condition. So it is also concerted for if it is E1, this is E2, this is E1. Now if it is E2, then it will be concerted mechanism, depends upon both base and halide. It is specific in nature, specific in nature means the say means it should be anti-parallel parent nature. So suppose we have the Newman projection of say a compound that is having a H here like this, then the X that is to be leaving, so this is the X that is to be leaving, should be anti-parallel planar from this. So if you look in the sidewise fashion, so this is H, so this should be X. Now this base will take this proton, and why it should be anti-parallel planar? Because suppose this is the bonding of this CX bond, there will be an anti-bonding in the back. Now since this is perpendicular to this electron cloud can get shifted to this anti-bonding, okay, and now it can form the double bond like this, and this X can leave. Okay, so this is the this is the mechanism followed for the E2. Now it requires of course strong base because the rate of reaction depends upon the base concentration also. Now say what is it is also moderately dependent upon the nature of this leaving group. It can happen in wide range of solvent. The most highly substituted alkane usually predominate, so this is the normal Sedgwick rule, but in some cases uses of sterically hindered base will result in the formation of least substituted product. So this is not much important for you. So for if you are using a say base which is much more hindered, then it will give a Hoffman product which is less substituted. While in Sedgwick, it will give more substituted say product. So this Sedgwick is a kinetic product. So this is just a higher information I am giving it to you, and this is a thermodynamic product. Sorry. This is a thermodynamic product because the reactant that will be formed is more stable because it is highly substituted. Now it is a kinetic product because it depends upon the steric hindrance on the reaction path. So it is a kinetic product. Now coming to this E1, so it will all depend upon the halogen, not stereospecific, so it can abstract proton from anywhere. Now it is cationic stability should be there, so benzylic, then allylic, then 3 degree and 2 degree. So this is same for substrate of E2 also. This is a common point to remember this. So not important, so it should be can be usually weak because already the X leave by itself. Very important, same as standard SN1. So it requires a polar protic solvent. So this should be kept in mind. So this requires a polar protic solvent. Now this we have a graph here. So this is a graph that we have of different type of reaction. So this is SN2. Now since it happens in one step only, so we'll get one transition state here on only, and then we'll get the product. The same is the case for E2 also. So one transition product and we'll get the required product. So this you can see that this is anti-planet of this, and an activated complex is formed ACT, and it happens in one step. So for unimolecular reactions, that is SN1 and E1, there is a formation of an intermediate that is formed here. So this is an intermediate that is forming here. Similarly, here is also a formation of intermediate. Okay, now this can happen in any way, so it is not stereo specific in nature, both of the reaction. And two transition states are formed on both of this. So you can consider the graph because it is important. It is given in CRT also for SN1 and SN2. So here was all about this SN1 and SN2. So let us just see a flow chart so you can decide that whether a given reaction will follow SN1, E1, E2 or SN2. So it is basically nucleophilicity versus basicity. So let us start this. So if it is a strong nucleophile or a strong base, so there are two cases. So since if it is, so let me make one thing clear here. So if something is good nucleophile, it is will also be a good base. So it is a common trait that is followed by all nucleophile or bases. So if it is strong nucleophile or strong base, then we will move in this direction. Then it will take this biomolecular reaction. So whether it will be SN2, so SN1 or E1. Sorry. SN2 or E2. So it is a very good concept. You can consider it for further means references also. So if you are taking a strong base or a strong nucleophile, it can only do SN1 and E2. Now comes different cases. If nucleophile is bulky, okay, so if nucleophile is bulky, it will give this E2. So then no doubt about it, you can simply take this E2. Okay. Now if it is no, if there is no, then it depends upon substrate. So if it is 3 degree, then it will give E2. It is 1 degree, it will give SN2, and if it is 2 degree, it can give SN2 and E2 both. So this is a flow chart for the strong nucleophile or strong base. Now suppose we are having a weak nucleophile and weak base. Then if 1 degree is present, then unfavorable reaction is unfavorable. Okay, the reaction will not take place. So if you are not using a strong nucleophile or strong base, then it is a substrate is also 1 degree, then there will be no reaction. So this should, both this condition combine, so this and this. Okay, then we will get no reaction. And if it is 2 degree, 3 degree, or stabilized 1 degree, so if it is stabilized 1 degree, say it is resonance stabilized, say it is hyperconjugated stabilized, so basically if it is stabilized, then in that case it will follow the unimolecular reaction. Okay, so it will follow unimolecular reaction. Now it will depend upon the bulkiness of this nucleophile base. So if it is bulky, then we will get E1 mostly, and if it is not bulky, we will get SN1 only. So here's a point, some point that you should remember. So if the nucleophile or the base is bulky, okay, then it will always say give this E1 or E2. Why? Because the reason is very clear. So if you have to attack, there should be some space to attack this. If it is no space, then it will give the elimination reaction, of course. A strong nucleophile, strong base with a bulky pack on its pack will give elimination reaction. Okay. Now let us move to some questions here. So here are some questions. So the synthesis of alkyl fluoride is best accomplished by, so which one of this? So you know the answer very well. It is Schwartz reaction, because Finkelstein is for iodine. Sandy we have not studied till now. And radical fluorination is not possible because FF bond is very strong. So you cannot do this radicalization of this fluorine-fluorine bond. The same thing is written here. So we're using an antimony or a salt of this mercury or a salt of this silver, and reacting it with this alkyl bromide and getting our final product, which is a fluoride, and it is called Finkelstein reaction. So we can have another reactant also. Sorry, this is called a Schwartz reaction. Okay, so if you want to make a fluoride, you can use a Schwartz reaction only and only Schwartz reaction, and if it is Finkelstein, it will not give you required answer. Now, what is the reason for not having this free radical fluorination? Because it is highly explosive in nature, so not preferred for the preparation of fluoride. Now, moving on to the next question. The addition of HI in the presence of peroxide catalyst does not follow anti-Markov's addition rule, because what are the reasons? HI is a strong reducing agent. HI is too strong to be broken or overlytically. I atom combine with H atom to give back HI, and iodine is not reactive across a double bond. Let us see the solution. So addition of HI in the presence of does not follow anti-Markov's rule, because iodine radical have more tendency to form I2. Okay, so we know that in the presence of this peroxide, the addition of HX follows the anti-Markov's mechanism. But if it is iodine, then it will not give the required product, because iodine quickly reacts with another I dot and we'll get this I2. Same thing is written here. Now question number 3 that we have here is nucleophile substitution, nucleophilic substitution, order of halogenation as incoming nucleophile is I minus, Br minus, Cl minus. So if it is the order of halogenation departing nucleophile. So this is the order of coming, and what should be the order of departing? So if it is a better living group, it will depart easily. If it's not a better living group, it will not depart easily. So this is the very thing, because the large size, the negative charges much more stabilized on the larger anion. And this is because the last side low electronegativity and nucleophilicity of this I minus. Now what is Wood's fitting? So Wood's fitting is 1 mole of aryl halide and alkyl halide. So I've taught you earlier a direct question we have from the JEE only. Okay. Now, which of the following bromide the correct order of SN1 is? So SN1 requires the formation of carbocation. It will be formed here. This one will be formed here, and this one will be formed here. So out of these three, this will be the most stable one because the double bond is resonating here. Then we have this 2 degree, okay, so which is more reacting, and this is SN1, okay. So we can say that we have B, C, and then A. So this is the order that we have. The same thing is written here because this is 2 degree allylic, then 2 degree, then 1 degree. Now here are some questions. You should do it by yourself. Okay, so I'm just scrolling them one by one. So by the following, choose the option. So what does what? So we know SN1 that represents two-step and give racemization. So it is true. Now bromination of alkene in alkyne diene halides, elimination of HX from alkyl halide. Okay, so we should can match this using this table. Now we have to see CCl was stronger than Ci. Why? Okay, so these are the reasons. More ionic, polar covalent, more covalent, or bond length is stronger. Which the following alkyl halide is used as a methylating agent? Okay, so of course, if you add methyl, suppose you have a nucleophile here, and you have to add methyl to it, so this will be the correct methylating agent. This nucleophile attack this CH3, and this Cl will leave, and you will get this NuCl plus, sorry, NuCH3 plus Cl. Okay, so this is the answer. This is the methylating agent, methylating agent. Now, which halide will be the least reactive in respect to hydrolysis? Okay, so which is the least reactive? So this have allyl radical with the most reactive. Now you can see it by yourself. I'm not giving you any hints because I've taught hydrolysis chapter with hydrolysis thing earlier. The hydrocarbon has a molecular mass of 72. It gives a single monochloride and two dichlorides and further photochlorination. The two dichlorides are. Okay, so you can do it by yourself. So these are the 10 questions that we have. So 5 I have done, 5 will do it by yourself. So tomorrow we will be dealing with this haloarine and this polyhalogen compound. So this was all for today. Thank you. If you have questions, you can ask.